Hello, YouTube. Today we're gonna discuss Newton's laws and Freebody diagrams. Dang, I hope you guys can see. First, we're gonna talk about Newton's laws. First, the first law is the laws of motion. An object in motion stays in motion, and the object at rest stays at rest, unless an abundant force acts upon the object. Example: the duck stays in motion. This rubber ducky. Oh, one of my friends got me this. The rubber ducky, as you can see, the rubber ducky stays in motion until an unbalanced force acts upon it. And as you can see on there, at the moment, the rubber ducky is at rest and continues to be at rest unless an unbalanced force acts upon it. That's the Newton's first law of motion. A duck stays in motion until, and so on and so on. Newton's second law is law of inertia, which is force equals mass times acceleration, or acceleration equals force divided by the mass. I should about have typed it out or whatever, but I didn't think about doing it, so I'm gonna go ahead and get a text box and add text. Force equals mass times acceleration, or acceleration equals force divided by the mass. This is probably much better. And then Newton's third law: every reaction has equal and opposite reaction. I push on the duck is pushing back at equal force. I do this, the duck is also pushing back at equal opposite force. Or I pull on this, and the string is pulling back at equal opposite force. Every action has an equal and opposite reaction. I should type action, but let's go ahead and move on to the next area. There's physics terminology. Mechanics is how a particle object behaves when a force is applied on it. Dang it, I also messed up on this one. Hold on. When a force is applied on it, basically it supports part of Newton's second law to where the ducky is moving because I'm making it move back and forth. The ducky goes up because I throw it up. The ducky goes down because I make it go down. This block, the block is holding up the ducky. A lot of that is mechanics related problem. Statics is when, oh dang it, I knew it. Yeah, let's face a bet. How many times go I mess this up? Dang it. How many times go I mess this up before this becomes annoying? But static is an object at rest or moving at a constant velocity. It's hard to explain, but you know why when I will explain to you mathematically. Force is mass times acceleration. When the object has a velocity, a constant velocity, the acceleration is zero. When acceleration is zero, by the Newton's second law, the force is zero. Even though it takes a certain amount of force to get something moving, technically, it will be zero. Force will be zero, means that it will have acceleration. Dynamic is when an object is accelerating, as in do that. One of the common problems you see in dynamics would be a satellite, because a satellite is constantly accelerating because it goes around the Earth and it's constantly in free fall. Static equilibrium occurs in. By the way, acceleration does not always necessarily mean go faster, but it could also mean the object changes directions. That's also another thing to keep in mind, because that's a common thing people make a mistake at. You assume acceleration is going fast, but if I move in a constant velocity going like this and then going like this, it's still acceleration because you're changing the direction. Acceleration isn't just about the speed of an object, but the direction it's going in. Static equilibrium is in a state to where an object is not moving remains at rest. Most of the problems on there is going to be at static equilibrium, or either static equilibrium or statics, because you're dealing with constant velocity, and net force is the sum of all forces. And the field body diagram is a diagram showing all the net forces. This is a free body diagram. You get the normal force, you get the mg or the gravitational force, and then you get the contact force or a applied force with is applied on the object. And all type of force you have is friction too, which is also common. For the beginner problems are gonna have problems that's in the friction for beginner purposes, but there are two type of frictions. There's static and there's kinetic friction. And most of it usually involve like date. This is a friction coefficient, and then that's the normal force, and that's the force of friction. There's static friction when the object is not moving, and kinetic friction which when the object is moving, but that'll be later on. Types of forces: contact force, involved by touching. Friction friction is a contact force because the blocks together, it goes against the surface of one or the other. Spring is a contact force, and anything involving normal force. A normal force is a contact force, and most normal forces are perpendicular to the surface. A non-contact force are forces that are in a long distance. Imagine having a long distance relationship where you don't really contact them as often. Not a good example, but I'm trying. And usually we got gravitational force, which is a non-contact force, and then we got electrostatic and magnetic forces. It's also a non-contact force. But you see that in physics too, or any form of physics or chemistry, because electrostatic involves how electrons interact. We have a problem now. Problem one: a 5 kilogram box is pushed across the room. What's the acceleration of the box? You got this pushed across the room. What's the acceleration of the box? It's 5 kilograms. Oh, shoot. And 20 newtons is being applied to it. What is the acceleration of the box? If you know Newton's second law, you get force equals mass times acceleration. Force equals mass times the acceleration. And if you do it algebraically, you want to find the acceleration, you'll find the m both sides. A equals force over mass. And then you take the 20 newtons over 5 kilograms. Before you get confused, a newton would be kilograms meter per second square. So you divide that by kilograms, will be the same as kilogram meter per second square times kilogram over 1. Delete that both sides and get meters per second square. 20 divided by 5 is 4 meters per second square. So that's this elevation. As a bonus, you want to actually, I don't want to say find the velocity or whatever. If you want to find the velocity of 5 seconds, you can use the kinematics or whatever. This velocity is at 0 plus AT. If it's in 5 seconds, you plug in V equals 0 plus 4 times 5. The seconds cancel out, and then you get 20 meters per second square. This box has a pretty high acceleration. The other problem would be 12 kilogram object appearances a net force of 36 newtons to the right. To the right. Oh, look. Similar type of problem I solved. This is pretty much where you have a whole box. I'm going to draw the box because... Oh, dang it. You got 36 Newton to the right, and the box is 12 kilograms. Now, first, we want to find the acceleration. F equals mass times acceleration divided by m, and you get A equals F over m, or 36 over 12 would equal 3 meters per second square. Now, we want to find B, if it starts from the west, what would the velocity be up to 5 seconds? If it starts from the west, what is the velocity up to 5 seconds? We learned what the acceleration is. A equals 3 meters per second square. And then initial velocity is 0. And then the time is 5 seconds. It's a kinematic problem. So now we got V, which equals VO plus A T. We got V equals VO plus A T, which equals 0 plus 3 times 5, and the velocity is 15 meters per second. We have successfully answered both problems using Newton's second law. Now, let's go to the free body section of it. Now, this time I'm going to use one of the 12 blocks or whatever. Oh, dang it. I might end up having to use like an extra thing. First thing we do is we draw a Freebody diagram. First thing we do, we draw a Freebody diagram. Let's see, shape this, and it is. I don't. Oh fudge! Hold on. Okay. Yep. We are gonna need to. Yep. We are gonna need to move to a nettle. Control V. So now we have a 10 kilogram box that holds on the floor. Huh. On the horizontal floor. And it is being pulled. It is being pulled to the right with 50 newtons. And the kinetic friction. I may have mentioned that before in the video. We got now first thing we're going to talk about is friction coefficient. Friction would equal the kinetic friction, I guess would be the coefficient of friction of that's kinetic times the normal force. So now we got like 3 forces acting on the object. Well, technically 4, because you want to count the mg, or the gravitational force. Want to count gravitational, but we got the n, got the w, we got the force of pull, and then you got the friction. And here's how. First, we already did the first step. We draw the Freebody diagram. Check. Second step is to calculate the friction force. W equals mg, which equals. You may think I don't have a vertical force because you didn't see newtons for that, but we do have a. Got it like 10 kilograms. And you multiply that by 9.8. And the total force for the weight of the force of gravity is 98 newtons going down. Newton. And in this case, you got the sum of f of y equals 0. And that will equal normal force minus. Oh, I missed last Wednesday. Oh well. Mg equals 0. Mg equals 98, so N would equal 98 newtons. So now we got 98 newtons for it. Now we can plug it into the 0.3 times 98. We would equal 98 times 0.3. 29.4 newtons. 29.4 newtons. So this is 50 newtons, and then this is 29.4 newtons. 29.4 newtons. And that's always the equate oval, even though it would be tempted to put 50 times divided by 10 and get 5 meters per second square for the third one. You don't really want to do that because you want to use a net force. Do that, we got 50 minus 29.4 newtons divided by 10 kilograms. And we got, oh yeah, I forgot. There's a donut about the acceleration equals F net over M. I forgot to mention that, or well, divided by 10, and the acceleration of the crate is 2.06 meters per second square. Let's be real. The next problem, I'll probably have to do the same type of stuff here. Oh, never mind. Now we got another problem, which is probably better than the last one, unless everyone wants me to do that. Hang by the force and it's at rest. It means it's in cycle equilibrium, which means that the net force of in the y direction is 0. So you have to treat the top of the board as a ceiling. For the heck of it. And there's not too much, and it's only one type of. There's only two forces that one there. One and two. Before you say that's a normal force, there's no normal force on there. There's tension force on the thing. And now you got 4 kilograms. So about 4 kilograms. Oh yeah, I forgot. Draw the equations equals 0 and f of x equals 0. And then you got the sum of y force, what would be the sum of f of y equals 0. And you got the tension minus mg equals 0. And they got the tension of the rope equals mg. And T equals 4 times 9.8. 4 times 9.8 will be 39.2 newtons. And that's the tension of the rope. We draw the Freebody diagram, and we got the tension of the rope. Problem solved. Now, the final problem, we are definitely going to need to do most of that on a net or slide. Let's see, test. Try the Freebody diagram, resolve the gravitational force into parallel components, determine whether the blocks move. Yeah, see, we don't know if the block even moves or not, so let's just go ahead and copy this, Control C, and go to the next slide, or next set of slide. Let's draw an inclined plane. Yay. Let's draw an inclined plane. That's going to make me happy right there with the little thing. And wait. You got a school. Ah, dang. Okay, good. How many slides would it take for me to explain this? I wonder. So we hopefully not too much. But we got a 10 kilogram box or block, whatever the hell you wanna call it. And you got mg. We got three forces. See the coefficient of static. Okay, so we got three. We got four forces. We got one. We got the force of gravity, the static friction. Oh no, we only got three forces because it's on west. And we got the normal force. So let's go ahead and label everything, even though I'm dead. There's normal force, mg, and f of s. Now, first thing we do is rotate the coordinate system. So let's go ahead and create a flat line. Let's go ahead and create a flat line. Go ahead and create a flat line. Got mg. Oh, dang. Go ahead and mg. Normal force and static friction and two other lines to try to describe it. The other lines are not important, they're just for my mental inventory. We got 30 degrees. Got 30 degrees. We got mg. When you rotate the coordinate system, when you rotate the coordinate system, joint angles usually changes. So you take that, you rotate it, and oh yeah, I got no. Okay, I got the gravity wrong. Dang it. The normal force is supposed to go parallel to the surface. I definitely should edit this part of the video. Sorry about that. Mg normal and static friction. First step is to draw the Peabody diagram. Second step is to note that this will be 30 degrees because you rotated the coordinate system. Or it might be it'll be 60 degrees. That'll be 30 degrees because of geometry. And now you got mg right there. You got the n, and then you got the f of s, and it's 10 kilograms. So now we got x coordinate and the y coordinate. Got up, odds, height. Now you got the n minus mg of cosine of 30 degrees equals 0. Sum of f of x equals 0. And I got sum of f of y is 0. And I got sum of f of x equals 0. We don't know that yet, so we have to stick with this one first. And we got n equals mg cosine of 30, which would be 10 times 9.8. 10 times 9.8 is 98 newtons times cosine of 30, which would be cosine of 30 is half, I assume. No, you get 98 times square of 3 over 2. And the answer would be, the normal force would be 49 to the square root of 3, or 84.87 newtons. We determine a normal force. Now, we determine the coefficient of static friction between the block and the incline. So now, we got the friction of static equals 0.4 times 84.87, and this will be 33.94 newtons of friction force. And it blocks west on the 30-degree incline. This is how many newtons the static friction is. And this is our answer. Now, does a box move or does it not move? Friction is purely an x component. But now we need to determine the horizontal force, since it's also going this direction too. So we got this as a friction. Friction is gonna, I forgot to include this. The friction going to reduce the sliding of it. So now to find the to find the movement of the x of x direction, and move f of x direction, we're gonna have to use mg sine of 30. Sine of 30 is half, So we get 98 times 0.5 will be 49 newtons. And the object and AS doesn't move. AS, if it moves, calculate its acceleration. So now we got 49 newtons in a x direction minus 33.94 also in the x direction. So now we get 49 minus this will be 15 newtons. So 15 newtons if you round to the closest number. Divided acceleration equals F net over mass. So get 10 and acceleration will be 1.5 meters per second square. And that is the acceleration of the block going down. A equals 1.5 meters per second square. We successfully answered 3 questions. We versus the 3 things, draw the Freebody diagram, put the gravitational force into parallel and perpendicular components. We know that the block moves, yes. And the acceleration 1.5 meters per second square. And this concludes this session of the physics.